Example, this is on page 97, problem 17, let's say, on 97. Let's read the problem first. Sketch the graph of an example of a function, f, that satisfies all the given conditions. So in this particular case, there is more than one correct answer. So sketch the graph of an example of a function that satisfies all the given conditions. So let's see the given conditions. We have limit of f of x as x approaches 3 from the right. They're giving us 4. We have limit as x approaches 3 from the left of f of x, and they say 2. We have limit as x approaches negative 2 from f of x, and they say it's 2. We also have f of 3, they say it's 3. And we have f of negative 2, and they say it's 1. So now they are saying to us, come up with an example. We can come up with many examples, but just one that fulfills all the given conditions. Any suggestions on how to start working on this problem? What do you think? And then I'm going to ask you, because although we only met twice, I think you have an idea of what I am going to do. Yes, Tom? Create a chart, create a table, summarize the information. I can't look at this and tell you what I should present. I have no idea. I want to summarize all the information in a table, and then it's going to be very clear and very straightforward. Good. Which x values do you think I'm going to put in the table? I know that that is a silly question. What am I going to put?
All the ones under the limits.
Of course, I'm going to put in 3 because they are telling me something at 3. And I'm going to put negative 2 because they're telling me something at negative 2. They're not telling me anything else. They're only talking in these 4, 2, what is 6? 1, 2, 3, 4, 5 conditions. They're only talking about negative 2 and 3. They're not giving us any other information. So let's look at negative 2 and 3. And let's take it step by step. So now you will understand that was the reason why I wanted to brush up on one more time on piecewise defined functions. So you understand those symbols that I'm using here. So this one says the limit of f of x as x approaches 3 from the right is 4. 3 from the right is 4. Done with the first one. Limit of f of x as x approaches 3 from the left is 2. Done with the second one. They're not telling us yet. I didn't get to that yet to see what's happening at 3. Ah, okay. F of 3 is 3. Done. So I have all the information about the action that is happening around 3. Now, limit of f of x as x approaches negative 2 from either side is 2. Done. And f of negative 2 is 1. I want to go back for a second to the piecewise defined function that we graphed together. We did not have that situation here. That's why these two symbols were touching. But here I cannot make them touching unless all these 3 numbers are the same, and then I only write a number. 3. But they're not the same. So the left-hand side approaches 2, the right-hand side approaches 4, but the actual value is 3, 3, the actual full point. Same thing here. It happens that these two are the same, but the value at negative 2 is 1. So obviously it's a piecewise defined function, there is no question. But I want you to understand that this situation here, those are, again, they're touching because this ended at 0, it started at 0. We did not have an intermediate value in there. So then I'm going to graph what I see. I will look at -2 and +3, and I will put the values that I have in my chart. It says as x approaches -2 from either side, the value is 2. Okay, fine. As x approaches -2 from either side, the function value is 2. However, function values approach 2, to be exact. However, at -2, the value is 1. So I'm completely done with -2 and the action around -2. Now, at 3, 3, is definitely this point. However, on the left, 3, 2. On the right, 3, 4. You can graph anything else you want, as long as you show that -2, 1 is this point, and the limits left and right are 2 from either side. You can you show that 3, 3 is this point. The limit from the left is 2, and the limit from the right is 4. What is the limit from the function that we just created? But make sure that you don't create a non-function. So you cannot, for example, connect this to the other side. That will not be a function by the vertical line test. Remember, by the vertical line test, any vertical line through the domain of this function has to cross the function in only one point. Okay? So this portion cannot overlap that portion and cannot overlap this one. So what is the limit of the function as x approaches 3 from either side? What would you say? Of course, because the left-hand side is 2 and the right-hand side is 4. Excellent. Any questions? Any questions? Okay, so coming back to our checklist for a moment. So this is pretty much one problem that you have to look at. Please, and before I forget, because I may forget, once we finish one section, redo the problems we did in class, do as many problems as from the odd number problems from that list of problems that my department came up with, and only then attempt the work in the checklist. Do not immediately go home and say, I'm ready. Redo the problems we did in class, do several problems, as many as you can from that list of recommended problems, and only then attempt the homework, please. Because otherwise you will forget. And it will not stick, okay? Any questions so far? Because I'd like to move on. Okay. Later on in this semester, we will prove what I'm going to write right now. We cannot prove it right now. We will look at the graph and we'll have an idea, but we have a method of proving it. Here it is. Limit as x approaches 0 from sine x divided by x. Every time we encounter something very important that will follow us in the future, I will always kindly ask you to commit it to memory. And this is from the previous lecture. This is a crucial situation, these two functions. Please commit them to memory. And this, the difference quotient, of course, commit this to memory. Okay? So now if I go back to this for a second and ask you to look at tangent for a moment. Just look at tangent. This is tangent. And I ask you, what is the limit of tangent as x approaches pi over 2 from the left? The limit of tangent x as x approaches pi over 2 from the left.
Positive.
Positive infinity. Awesome. What will you say the limit of tangent x as x approaches negative pi over 2 from the right? Negative infinity. Later on in this chapter, not today, I will ask you, but you can already answer. As x approaches infinity, what does arctangent approach? Pi over 2. As x goes to negative infinity, what does arctangent approach? Arctangent x approach. But that's a little bit later, and it's about horizontal asymptotes. This is about vertical asymptotes. Good. So that's why please commit this to memory. And now I'm going to ask you about this to commit it to memory. We cannot prove this right now, but we will look at the graph and we'll come up with an idea. But we will prove it later. It's very simple. But we don't have all the information yet today. So clear everything and put in sine x. Close the parenthesis and divide by x. A question before we look at the graph. Do you think that this function exists at 0? Of course not, because 0 is in the denominator, so it's actually when I replace x by 0, how much is sine 0? That is cosine. So it's 0. 0 divided by 0. I'll talk about this in a moment. So let's look at the graph. Every time we are asked to find the limit, we should always, although I'm going to say something that you will say, well, this is a contradiction. This is not what you said last time. Remember when I said h approaches 0 and I said not 0. It's not equal to 0, but approaches 0. And I said clearly not equal to 0. But now I'm going to say when we are given a limit, we have to plug in the number we have. We are asked to determine the limit for. Only because we have to identify the type of limit. Okay? Not because we say that x is 0. We can't say that. Okay, so we're ready to graph. And since I'm interested in what happens around 0, I'm going to change the viewing window. And I'm going to say, well, I only want to see between -2 and 2 for x. And between a scale of 1 is fine. And y minimum between -2 and 2 as well, with a scale of 1. There is one very important item that we have to remember. We only use radians in calculus. So make sure that it's obviously clear, it is, but make sure that your mode, go to mode, and make sure that you have radian mode, not degree mode. So go to mode, make sure it's in radians. So now finally, let's go to graph. Click on graph. The software is already showing it. Okay. So one more time, you do see a little blimp here, obviously, because the function is not defined as 0. So I'm now going to ask you to identify this limit. This is what we are asked to determine. Sine x over x. Limit as x approaches 0. And let's look again at the graph, and let's come up with a decision. Of course. It is 1. The limit is 1. Again, later on, we will prove this in a different way. Much easier than even plotting it in, graphing it. Now, initially, so forget about 1 for a moment. Initially, I have to do this. Sine 0, 0. Replace x with 0, 0. 0 over 0 is called indeterminate. Indeterminate case. Let's say 5 divided by 0, it's called. Thank you very much. The 0 over 0 as an indeterminate case has hope. I say, in other words, there is hope, meaning the limit may exist. I'm not saying the limit exists. I'm saying the limit may exist. Limit may exist. The undefined situation has absolutely no hope for the limit to exist, of existence, of the limit. When the limit does not exist, there are three possibilities: DNE, infinity, or negative infinity. In any of the indeterminate cases, the limit may exist. There is hope. They are all listed at the end of this. We're going to discuss all of them. There is a total of 7. On the last page of the checklist, I listed them for you. Summary of indeterminate cases. 2 ratios, 3 types of powers, 1 difference, and 1 product. All these 7 indeterminate cases have hope. So if we're asked to find a limit, and it turns out that we run into any of these 7 cases, the limit may exist. No guarantee, but the limit may exist. So this is the first one we are discussing right now, 0 over 0. In this case, the limit will never exist. If it's a number over 0, not 0. That's why I chose a number at random, 5. So if it's a number over 0, there is absolutely no hope. The limit will never exist. It will be one of these situations. Okay? Now, what is important about this limit? And you can say, okay, so it doesn't seem that it's such a super important type of limit. It is. This is more like, if you want, like a law, I would call it. It has to be understood in the following way. So it's beyond just a simple function. As long as all these 3 quantities are identical, the limit will always be 1. And also the multiplicative inverse. So limit I also put it on the checklist. It's on page 2 at the top. And this is a very important type of situation that we are looking at. So I tried to mimic this. It didn't really work very well. Sorry about that. So let me give an example. Let's say we want to determine limit. So this is an example. Limit as x approaches 5 from sine x minus 5 divided by 3 times x minus 5. So I'm going to look at this and remember that as long as I have the same quantities here, here, and here, these 3 have to be the same, 1, 2, 3, and 0 here, not 5 or 10 or negative 3, very important. So 3 same quantities and 0 here, then the answer will be 1 for something like this. So now let's see if we have all these 3 conditions fulfilled. 4 if you want. So this, yeah, this is fine. This is x minus 5. Do I have x minus 5? So I do have this piece. Do I have x minus 5 in the denominator? Yes, I do. I do have this piece as well. Now the question is, do I have this? I can subtract 5 from both sides. So x minus 5 approaches 0. So I do. If I tell you x approaches 5, I really mean x minus 5 approaches 0. It's the same thing. So now all 3 conditions are indeed fulfilled. Yes, I do have an extra value in here, but it doesn't really matter because all those conditions are fulfilled, and I know that this limit, when the quantity approaches 0, this limit must be very good. And all I have to do is incorporate that extra value in there, and now in this case the limit will be, that's it. as long as I commit this to memory, because this is very important. It's a very important type of problem. Here's another example for the same thing. Let's say we have limit as x approaches 2 from x squared sine x minus 2 divided by x squared minus 3x plus 2. Now you can say, oops, what do I do now? Please. Of course. Of course. That's why it took me a second to multiply. Of course. So, limit, I can change this into x minus 2 approaching 0. X squared can stay and wait for me. Sine x minus 2 can stay and wait. But now, yes, let's try and factor the denominator. What do you hope to get in the denominator? Right. I hope to get an x minus 2. What else should I get in there? In this case, I get an x. That's it. So now, so remember, x minus 2 approaching 0 is the same with x approaches 2. They are exactly the same. So now I'm asking you, where does this go? Because I have 1, 2, 3 fulfilled. What will this go to? 1. And now, where does x squared go when x approaches 2? What do you think? No. When x approaches 2, just let's graph it. We don't know a lot of that yet, right? So this is x squared. As x approaches 2 from either side, what will the function value approach? 4. When x approaches 2, what will x minus 1 approach? 1. So then the limit in this case is 4. But all this happened because we remembered a very important property, if you want, or a law, if you want, or the limit of sine over the same quantity when the quantity approaches 0 as being 1. Any questions? Any questions?
Does this only apply for sine?
Yes, and we do have another limit for cosine a little bit later. Yes, yes. Okay, so let's look at a couple of limits. I would like to talk about infinite limits. Infinite limits. So let's start with limit as x approaches 3 from the left of 2x plus 1 divided by x minus 3. We're asked to find this limit of a function as x approaches 3 from the left. Although we said when x approaches 3, we know that x is not 3, we will plug it in just to see the type of limit. Maybe it's an indeterminate case, or maybe it's an undefined case. I need to know the type of limit. Like we did before. Here's what I did. When we were trying to determine sine x over x, I said when x is 0, sine is 0. When x is 0, x is 0. So the limit is 0 over 0, which is an indeterminate case. And then I know there is hope. So now if I plug it in and I get something like this, I know there is no hope. And I have to select the correct answer. So if I get something like this, I have to select the correct answer. If I get something like this, I'm still hoping. Okay? So there may be different techniques. And there will be a lot of techniques there. Don't forget to bring the limit packet that I created for you next time. Okay. So I plug in 3. 2 times 3 is 6. Plus 1 is 7. Okay, so this is a positive value, 7. And then 3 minus 3, and I get 0. And I say, whoops. I know that no one can help this limit. It's definitely one of the 3 options, infinity, negative infinity, or D and E. There is absolutely no hope. What is my next step? I have to select one of the answers. Here's what I do. 3 from the left. Give me a close number to 3 from the left. You will say,
2.9.
excellent, 2.9. The numerator is still positive, no matter what. But 2.9 minus 3, what type of number will that be? Negative. So then I know exactly which one of these 3 to select. Which one will I select? That's it. Negative infinite. Okay. Let's look at 37. Any questions on this previous limit? 37 on page 98. We have limit. Sx approaches 2 from the right-hand side, from x squared minus 2x minus 8 divided by x squared minus 5x plus 6. And of course, I will plug it in to see what type of limit this is. Because maybe I plug in at the top and I get 5. I plug in at the bottom and I get 3. And it's 5/3. I don't have to do anything. So at any point in time, whatever type of limit, whatever limit I'm given to determine, I have to plug it in. Although initially, if you remember, I said, do not. This does not mean that x is 2. But we have no choice. In order to determine the type, we have to plug it in. So 2 times 2, so this is 4. 4 minus 4 is 0, minus 8. So the numerator is negative 8. 2 times 2 is 4. 4 minus, so 4 plus 6 is 10, and 10 minus 10 is 0. Oops. So again, an infinite limit, possibly D and E. It's not the case. If it's from the right-hand side or left-hand side for a rational function, it's not going to be a D and E. It's not that oscillating situation. So it's just a rational function. So I know that I will have to select one or the other. I'm going to try and see if I can get rid of something. Maybe there is some factor that I could get rid of, and that will make it much easier to determine. So is there any way we can factor the top? Good. So let's factor the top.
It would have to be -4 and +2.
So x minus 4 and positive x plus 2. Awesome. Now, I want to make a very important point here. When we plug in 2 in this expression and we get 0, do we remember anything from pre-calculus that happens mandatory? If you give me a polynomial and say to me, plug in 5, and I plug in 5 and I get 0, what does that mean about the polynomial? What does it say about the polynomial?
It intersects the x-axis.
No? So let me give you another example. You're saying 27, and you ask me, is 3 a factor of 27? I'll say 27 divided by 3 is 9, remainder 0. Yes, it's a factor of 27. So now I'm coming back to my previous question. I have a polynomial, and you say plug in 5 in it, and I get 0 when I plug in 5. What does that say about the polynomial? What does x minus 5 represent for the polynomial since the remainder is 0?
There's a factor of 5.
That's it. That's all I wanted. So when I plugged in 2 in this polynomial and I got 0, which factor must be in this polynomial no matter what?
X minus 2.
Awesome. It has to have an x minus 2, otherwise it will never be 0 when I plug in 2 in it. So this is a combination of the remainder theorem and the factor theorem. If the remainder is 0, then the quantity is a factor. So what is the other one?
Minus 3.
Good. Well, it turns out that I can't simplify anything. X minus 4 and x plus 2 and x minus 2 and x minus 3. I was hoping that I can make it simple. But the discussion we had about this 2, it will come back over and over. So when I plug in 2 and I get 0, x minus 2 is the problem. is the factor that creates that 0. Okay, so all I have to do is just plug in 2.1. So this will not help me but to simplify, but it will definitely help me in identifying the sign, because this is so much easier now. The numerator is definitely negative. So 2.1. 2.1 minus 4, negative. 2.1 plus 2, positive. 2.1 minus 2, positive. And 2.1 minus 3, negative. It is much easier to work with factors and determine the sign than with those two polynomials. But it's the same thing, really. So one more time. 2 from the right, a close number to 2 from the right is 2.1. I only need the sign. 2.1 minus 4, would you agree is negative? 2.1 plus 2, would you agree is positive? 2.1 minus 2, would you agree it's positive? And 2.1 minus 3, I hope you agree it's negative. I have two negatives. The positives don't even look at. There is no point. So then the answer is? So the positives don't count, and we have two negatives, right? So it's positive infinity. So as we discussed a few minutes ago about tangent, if the limit of a function as x approaches 3 from the left is negative infinity, what does x equals 3 represent for the function? Okay. I know it's a lot, so allow me to go back to our graph. Remember, I asked you, now I can't find it, it will take me, okay, here it is. So vertical asymptote, correct. So as x approaches pi over 2 from the left, the function values go to infinity. X equals pi over 2 is a vertical asymptote. As x approaches negative pi over 2 from the right, the function values go to negative infinity. Therefore, there is a vertical asymptote, x equals negative pi over 2. Same thing here. As x approaches 3 from the left, for this function, we get negative infinity. X equals 3 must be a vertical asymptote. Limit of a function as x approaches 2 from the right is positive infinity. What should I write? That this implies what? Same thing we wrote for this function.
X equals 2 is a vertical asymptote.
That's it. It's sufficient for one side. I don't even have to check the other. If the limit from the right is infinity, there is a VA. I don't care what happens to the limit from the left. If at least one of those is infinity, then the function has a vertical asymptote. Tommy had a question?
I'm just thinking in the case of negative.
It doesn't matter. Remember the tangent, right? So if we look back, so here it goes to negative infinity, and this is x equals negative pi over 2, a vertical asymptote. Okay, so I like to start 2.3. We will not be able to finish it. And between now and Tuesday next week, please finish page 1, page 2, page 3. If you need examples, this is not due yet. But if we wait till we finish the entire chapter, this is going to be very difficult to complete. So page 1, 2, 3, 4, 5 at the top. So we're not going to be able, we only have 5 minutes left, 6 minutes. So I just want to list some limits for you. So the first 5 pages, please finish them between now and Tuesday. Remember how? Redo all problems we did in class. Do the odd number problems from the handout for recommended problems. Check the answer in the back. If you discover something that you think we have not looked at, they're all different. So if you think that we haven't finished, I'm starting 2.3. Please, 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 please. Okay? So come back to class and say, I would like to see an example like this or an example like that, and we'll make one up. So you have a complete information. So 2.3, limit laws. And this is my page 8. Okay. As I mentioned here, you don't have to write them if you don't want to in this packet. I think that you should hold on to the packet because it has everything in it. There are 11 limit laws. 11 laws. Now, they make no sense and they cannot be applied unless we have these conditions. Limit of f of x as x approaches a from either side. I promise I will finish in 5 minutes. Exists and is a number that we are going to call it L. Limit of g of x as x approaches a from either side also exists. When we say that the limit exists, we mean it's a number, not infinity or DNE, of course. And let's call this M. So these are the conditions for the limit laws. If these conditions are not fulfilled, we cannot apply a limit law. So here's the first limit law. The limit of a sum of functions as x approaches a from either side is the limit of the first function plus the limit of the second function as x approaches a from either side. This is not a distributive law. Do not consider it a distributive law. It's not. It's a limit law that says the limit operator applied to a sum of functions is the sum of the two limits. Let me give you an example in which this does not make sense and it cannot be applied. Here's an example. So if we have limit as x approaches 0 from either side from 1 over x plus 3x, I am not allowed to write limit of 1 over x as x approaches 0 plus limit of 3x as x approaches 0. I am not. I am not allowed to apply the limit law of the sum. Can anyone say why? Why come? How come that I cannot apply it? This is very clear, right? F is 1 over x, g is 3x. I'm allowed to do this, but I'm not allowed to do this here. Why?
Is there directional?
No.
Not a single term?
No.
The limit of 1 over x
Does not exist. The limit of 1 over x as x approaches 0 from either side does not exist. So another function that we have to commit to memory, here it is. This is the graph of 1 over x. Very important function. The graph of 1 over x. As you see, the limit from the right-hand side of 1 over x is infinity. The limit from the left-hand side of 0 for 1 over x is... So what is the limit from either side? It does not exist. Therefore, we cannot apply the limit law for this function that I created. Can I apply the limit law for this function? Let's say I want also the difference. The difference is also a possibility. So let's say I want 3x minus 4 as x approaches 2. Can I write limit as x approaches 2 from 3x minus limit of 4 as x approaches 2? Yes, because both limits exist. What will be this limit? As x approaches 2 from 3x. What will that be? 6. What is the limit of 4 when x does whatever? I don't care what it does. It's 4. So then the limit is 2. So in this case, I was able to. Of course, we have the limit of a product, which will be the product of the limits. So limit of fg as x approaches a. What do you think? A wild guess. What do you think this will equal to? Limit of f times limit of g. The same with the sum and the difference, they're the same. What do you think the limit of f over g when x approaches a will equal to? Yes, limit of f over? Correct, very good. As x approaches a, but I have a comma here, and I have an if here, which I did not have before. What am I getting at?
It's the limit of g is not 0.
Exactly. Since we denoted this by m, I'm going to say if m is not 0. And of course here you can go back and replace L and M. So this is L plus or minus M. And of course here this is L times M. And of course here this is L over M. Have a good holiday.